Okay. Yeah, so today let's talk about circumference of the ellipse. We often or we clearly know what perimeter of closed curves are. So let's talk about what is the perimeter of an ellipse. And often if we are not already aware of it, we might take for granted that there exists a formula like the simple formula for circumference of a circle, 2 pi r. But remarkably, there is no such straightforward expression for the circumference of an ellipse. So let's go about this in a simple manner. And when I say there is no simple expression, there is no rational expression for that. There is no closed form expression. It's given in terms of an integral. That's what I mean. So I'll come to that. So let me slowly motivate this. So let's begin with circle, right? So circle is so we have circle, and clearly circle. What we mean is that take a point and think of all other points which are equidistant from here. So this is a set of points which are equidistant, and let's say the distance is r. And we would like to know if you were to cut this point here, open it up, and measure the length of that curve. That's what we mean by the circumference. So circumference, and it is the same as perimeter. And circumference for a circle is equal to the diameter times diameter is 2 times the radius times pi. So it is often written as 2 pi r. And it's remarkable that the length of this curve divided by the diameter comes out to be a number that we very, I think, more than 2,000, at least 3,000 years back, probably they defined it as pi. I don't know the exact history of this, but that's what we are talking about. We would like to know this number, right? It is easy to guess that it will have a radius because there is no other scale. Circumference is a length. It has to be in terms of r. So dimensionally speaking, that has to be this r. But this number 2 pi, you have to come up with in some manner. Let's do this in two different ways. Let's just stick to the circle, and then I'll come back to the ellipse. So one could be the geometric form, and one could be the algebraic form. We will assume that the triangle properties are known. We have sine and cosine already well defined. And one possibility is that we use the idea of calculus or algebra if you want. And it is remarkable that algebra was not as a field. Like when I say algebra, I really mean when we say x, right? Whenever we write an equation in terms of x, for example, when I say the circle is x square plus y square is equal to r square, those equations were not written down or not available before 16th century. So they're very, I mean, reasonably recent. Like in that sense, whenever we say there is an algebraic proof for the circumference of a circle or the calculus proof, that was not available before that. So, and whatever is before that, we can very broadly say it is geometric, right? So that's one way of looking at it. So let's think about a geometric proof. That means that I'll try not to use calculus into it. And one way to find the circumference will be like divide this into, let's say, a pentagon, make a pentagon out of this. So that's a pentagon. Right. So that's a pentagon, and that's your radius r. And this will be angle theta. So theta will be equal to, we already know the idea of 2 pi. Notice that I'm using the idea of 2 pi. That's already known, divided by how many sides. If this is a pentagon, there is 5 sides to that. But if I want to measure the, let's say this is half of that, right? So that's the angle theta. So I will measure this distance multiplied by 2 and then multiplied by 5, right? So n will be equal to 5, let's say, if it's a pentagon. So it is 10 times that. So that's my x if you want. So that's 2 times n, right? So if I can calculate this x and multiply that by 2 times n, I should get my circumference, correct? So circumference in this geometric picture will be, so it is 2 times n times x. And x would be, again, we are using the idea of a right triangle. So this is a right triangle. So x would be r sine theta. Right? So it is 2 times n times r sine theta. And that gives us, let's see.
Is it background?
Am I?
Mine is okay.
I'm getting a. Is it from my?
Oh,
Is it from my end? I'm hearing. Is it? Yeah.
it could be
Maybe
from my end.
Yeah, maybe it is picking up some distant voices, probably. Yeah, that's okay. Yeah, yeah. Now it's, I think, gone. Yeah, okay. Yeah, maybe. But whenever you want, I think you can just put on unmute yourself. I think that should be okay, right, Rishi?
Yeah. Actually, there was somebody in the neighboring room. So
Okay. Yeah, sometimes this mics pick up from wherever they want to. Yeah. Okay, so circumference, I think, will be 2 times n times x, and we can say n is equal to 5 or n equal to 6 for a hexagon and so on, and theta would be equal to pi over n, right? So I can say this will be 2 pi r times sine of theta, which is pi over n, and divided by pi over n again. And one can see that, of course, now with all our knowledge of sine theta over theta, in the limit n tends to infinity, this surely becomes 1. But one can also see that if this is a circle, you can also use this to put some bound on the circumference. Like you can say that this is another pentagon you can build. This will be an outside pentagon, right? And this is, the circle is going through it. Maybe I should draw this better. So I can have a, let's say, a triangle, and this will be also a triangle. So these are 2 triangles that is enclosing the circle, and if I had a polygon, equal sided polygons, then I can get an outer, the upper limit on the circumference and a lower bound on the circumference, and that's so this will be greater than that. So one can write that C will be greater than or equal to, in the limit, extreme limit, where it is 2 pi r times sine of pi over n over pi over n, and it will be less than or equal to, if you were to take the outer one, it becomes, this is your radius, so you have to get the tangent, so it turns out to be tangent of pi over n over. And of course, in the limit n tends to infinity, it really captures this out. So that's a small motivation that, okay, one can do this without calculus, but let's use calculus at this point, or algebra in a sense, and let's try to do this again using that. And later, when I do the ellipse, I'm only going to do it using the calculus method. I it will be nice if I can get something like this, but I could not think about it sufficiently. So let's do the same circumference now using calculus. So you now say that you know the equation of a circle. So x square plus y square is equal to r square, and that's your y, that's your x, and that's your circle. So circle can be broken into 4 parts, and we are interested in the length of this curve starting from here to here. So some arbitrary point here would be x comma y. So the circumference will be 4 times the length of this curve, which we will say is ds, and going from here to here. At this point, I did not say the limit. It's understood that it is going from this point to that point. Take an arbitrary small element here, and let's say that's ds. And in the extreme limit, so this tiny element can, in the extreme limit, become a straight line. So we are taking the calculus limit. So this is dx, that's your dy, and that's your ds. So we say ds square is equal to dx square plus dy square. In the infinitesimal limit, that's true. So we can say ds is equal to dx times 1 plus dy by dx, the whole square. And we clearly see that if we know the slope of this curve at every point xy, it actually tells us information about ds. So this is equal to 4 times dx times 1 plus dy by dx, the whole square. And this is 0 to, I have to go from x equal to 0 now all the way to r. That's my expression for the circumference. What is dy by dx? Let's rewrite y as r square minus x square, and dy by dx then is equal to, I start with a 1 by 2, goes in the denominator, r square minus x square, 1 by 2 minus 1 is minus 1 by 2, and then there is a minus 2x. So that's minus x over r square minus x square. We are interested in the square, so the negative sign doesn't really bother us. So this is 4 times 0 to r dx, and you have 1 plus x square over r square minus x square. Simplify this, and we get 4 times 0 to r dx times that is r that comes in the numerator over r square minus x square. Right, r square minus the x squares cancel out. I can make a simple substitution. So x equal to r sine theta is a simple substitution you can make. And in that case, the lower limit when x is equal to 0, theta is equal to 0. And in the upper limit, when x is equal to r, theta is equal to pi by 2. And dx is equal to r times cosine theta times d theta. So I have r cosine theta, d theta. I already have another r there. And in the denominator, I have an r square minus r square sine square theta. R square minus r square sine square theta is cosine square theta, and this pretty much cancels the whole of denominator. So that cancellation plays an important role. D theta goes from 0 to pi by 2, so I have 4 times r times pi by 2, and that's 2 pi r. So it's true. That's the simple idea that the circumference of a circle is 2 pi r, which we already saw using a geometric proof there. But now we want to sort of repeat this for the idea of an ellipse. First, let me define what an ellipse is. In the same spirit, I'll pretty much repeat the same spirit, except the geometric proof that I did here, where I took a polygon and tried to capture the circumference of a circle. That analog I will not have for the ellipse, but I will define an ellipse using the idea that it will this time be equidistant from 2 points, and then do a similar proof here. And then we have to do this integral, right? Here, the idea was that this integral was doable, and we will see that there will be a challenge we will face there. Any questions here at this point? Any comments or anything? Yeah, pretty.
Yeah, Shajesh. Yeah, this
Yes.
is nice. I was just thinking that, this is a nice example to like when we teach students polar coordinates to do problems in polar coordinates. See, generally when they are done from their +2, they have been using this Cartesian coordinate system, right? So in mechanics, they resolve the forces and accelerations in the x and y directions and solve this component in x and y directions. But in polar coordinates, of course, you resolve in the plane polar coordinates, you resolve in terms of the r and theta, right? The radial and tangential components. And we always say that, you choose horses for courses. If you have a circular geometry, then the Cartesian coordinates are a long haul, and polar coordinates almost trivially give you the answer because you have chosen the coordinate system that fits the. Now here, if the ds is written in terms of the polar coordinates is r d theta, r just factors out, d theta goes from 0 to 2 pi, and you trivially get the answer.
Good point. Yeah, so let's see. Yeah, that's correct. Yeah, very good actually. Yeah, so why do all this, right? If you do the, perfect. Yeah, so ds square, there would be.
No, you just write
see.
ds. Just write ds.
DS
ds would be r d
is
theta.
If you're on the curve, but first I should write a ds on the plane, right? Probably.
No, but we
I think
see here we are going to be our ds is on this curve, right?
Yeah, you're right. I'm just going to write it like this. And
yes,
now on the curve, this is equal to 0, right?
Exactly.
So this is equal to 0 on this on a circle. So ds is equal to r d theta. So r is fixed. In fact, this is r now.
Constant,
r d theta. Yes. And when I integrate, it is 4 times r d theta. Integral is 2 pi pi by 2 now. So straightforward. Exactly. That comes in 2 lines.
No, you don't even have to do 4 times. You keep the whole circle and take the theta from 0 to 2 pi, right? So not even have to do 4 times.
Perfect.
So
perfect.
So I mean, I think this can be a beautiful example to illustrate to students that although this when we do it in the x and y coordinate system, both x and y vary, right? So it sort of gives an impression that this is a 2-dimensional problem, but there's a constraint x squared plus y squared is r squared. So it's effectively 1-dimensional problem, and polar coordinate just are the perfect coordinate system because only theta is varying, r is fixed. So you actually have a 1D problem which you solve using a coordinate system where it becomes 1D problem. And it becomes trivial. So you don't even have to do this integral, you don't have to go to this, what is this integral? You can just straightforward, I mean, integral is trivial now, then it becomes, so it's a beautiful illustration, that how geometry can ease your, choosing the right coordinate system appropriate to a given geometry can ease your, simplify.
Yeah, for the appropriate purpose, use the appropriate coordinates. Yes. And we'll see, maybe we should attempt that for ellipse too, because I think we might be able to write the equation there. And let's, good comment. Good thought. So let's see this. Okay, cool. So now I want to pretty much repeat this for an ellipse, right? That's kind of understood what we're
Yeah.
going to do, and see if there is any nice thing we can do. Yeah, okay. So now we say an ellipse. So ellipse, now we will define, let's say there is 2 points. Like earlier we had 1 point, and we now say that think of all points which are such a way that the length that you build from here, so this total length, this plus this, how can I write this? Let's say capital or alpha plus beta, let's say. We want to say all points such that this is a constant. Earlier we said that we picked 1 point and all points which are equidistant from that, that is constant. Here we are saying alpha plus beta is a constant. Let's have a coordinate system. Let's say this we choose is f comma 0, and this will be minus f comma 0. So I'm doing algebraically at right from the beginning itself, so that I can get the equation in a more reasonably easy manner. Somewhere in between it will become reasonably long, so I will just write down the equation. So this is my x comma y, and we want to see all possibilities. So it is clear that x plus, so the distance alpha will be x plus f square plus y square, and beta would be x minus f the whole square plus y square, and that has to be equal to a constant. So that's our, in principle, an equation of a ellipse, but this can be simplified. It's clear that when y is equal to 0, so let's say this is x and that's equal to y, and if you were to do this, it's clear that, I mean, or I'm kind of going ahead here. Let's say when you really stretch this here, this point is A and this point is B. So if I set y is equal to 0, I get this point, and there it is clear that the total length is now, this is 2 times or A plus f, right? So this is when x is equal to A then my equation tells me that it is x is now A, so it is A plus f and plus A minus f. So y is 0, this is A plus f, A minus f. So that's equal to a constant, and that tells me that constant should be equal to 2A. So that's equal to 2 times A. I can also learn one more thing, that if I were to set x equal to 0, then y could be equal to b. So let me say that's the point b. This is called the major axis, and the b will be called the minor axis. And then we know that what is the length now? So this will be x is 0, so this is f square plus b square, and there are 2 of them now, so that's square root of that times 2. That's equal to, here we have constant was 2 times A, so that's 2 times A. So 2 cancels out, and we learn one more equation, that f square is equal to A square minus B square, or you can say f square plus B square is. So that's a property you can learn. Now, if I want to now get an equation for an ellipse in the usual standard rectangular coordinates form, I have to now expand this out, put the constant to A, and pretty much it explodes, but it is not very hard, about 7 or 10 steps down the line. So let me at least go a few steps, and then, so if I were to square one side, I get x plus f the whole square plus y square plus x minus f the whole square plus y square plus 2 times square root. Just being lazy here, I'm not explicitly writing that, and that will be equal to 4 times a squared. Bring this onto the left. So there's some cancellation here. So I immediately get that 2 times x plus f the whole square plus y square times x minus f the whole square plus y square is equal to, I get 2 times a square, right? 2 I'm canceling out everywhere. So x square, there are 2 of them. So it's minus x square
But
minus y square.
you didn't cancel the 2 on with the square root.
Oh, I did not cancel the left on the left side, so I cancel it out here. Yeah. And that is an f square also, right? So it's a plus f square, so that's minus f square. You have to square this again, and so this is the step I will skip. Right? It's not very hard, just few more steps, and you can do the algebra, and it comes out reasonably straightforwardly that you get x square times b square plus y square times a square is equal to a square b square. Writing it this way, you kind of see where it might be coming up. There is an x raised to 4 term, there is an x raised to 4 terms here. All of them cancel out pretty nicely, and these are the terms that were left out. Very cleanly it comes out, which immediately gives you x square plus a square plus y square plus b square is equal to 1, which is the equation of an ellipse. And notice at this point, since Rishi pointed out that there is a polar coordinates also possible, and the equation for an ellipse in polar coordinates is usually written as, and it is good to point out a couple of things there. So again, so I have f square is equal to a square minus b square, and that's the only condition I put, I guess. Yeah, and that's your equation. If I were to now, instead of choosing this as my origin, if I choose one of the foci as my origin, so that's my R. So this is my origin. Notice I'm moving my origin. Earlier it was x equal to 0. And then my equation of an ellipse is R is equal to some constant R naught, which I don't remember at this point. It will come out to be in terms of A and B, because those are the only 2 properties. And this will be 1. So it has to be somewhere less. So there is 1 plus or minus basically E cosine theta, where E now, I think E I remember because I use that here. E is equal to 1 minus b square over a square. That's called the eccentricity of an ellipse. R naught, let's see, can I get this out of this? Maybe it is related to 2a. So at theta equal to 0, let's say theta equal to pi by 2, right? No, theta equal to 0, I have f plus a, right? So theta equal to 0 is, it's down here. Yeah, so at theta equal to 0, it is 1 plus e. So what is a? Let's see. Help me here.
You can just go ahead and do whatever you were saying, right? Theta equal to 0, it is
Yeah, I was just going to do that. Yeah, theta equal to 0, R is f plus a, right? So it is f plus a is equal to R naught So this is theta equal to 0. R naught times 1. I want it to be minus E because one will be less and one will be large, right? So it is 1 minus E, right? So this length will be larger than the other length. And at theta equal to pi, so let me see if I can. So at theta equal to pi, I will have this to be A minus F, correct? So this is just A minus F would be R naught divided by 1 plus E, I suppose. Okay, so I can get R naught, I suppose, out of this. If I add these two equations, so I get 2 times A is equal to R naught 1 over 1 minus E plus 1 over 1 plus E, correct? And 1 plus E. So this is 2 times R naught over 1 minus E square. Right. And 1 minus E square here is, we said in terms of E. So 1 minus E square is B square plus A square. So we have 2 times A is equal to 2 times R naught. 1 minus E square is B square. 1 minus E square is B square over A square. Correct. I guess A cancels out. So I have R naught is equal to B square over A. Better? Yeah, so equation of a ellipse in rectangular coordinates where the origin is right at the center of the ellipse is x square plus a square plus y square plus b square, and in polar coordinates it is b square over a divided by 1 minus I think I chose it to be minus, okay, 1 minus e cosine. Okay. I think that's what it is, yeah. And maybe we can try using both what will come out to be the perimeter of the ellipse. I did not attempt the polar coordinate construction for this talk, but I can attempt on it at the end. But let's first do the rectangle coordinate. Yeah, so only thing I was trying to point out is that this is an additional thing I just presented, but equation of an ellipse is x square plus over a square plus y square plus b square is equal to 1. Did I confuse going around?
Oh, fine.
No,
So,
that
Shajesh,
is
here
what-
we started with this formula, right? E is, you started with this eccentricity formula, right?
Yeah, so the only thing I said is that I took 2 points
Hmm.
and I said I want a set of points which such that alpha plus beta is equal to a constant. And I went through that algebra and said that the equation for such a curve will be x square plus a square over a square plus y square over b square is 1.
Hmm.
But then I said that, oh, what will the equation be for a in rectangular, sorry, in polar coordinates?
Hmm.
And in polar coordinates, I did not derive it. I immediately wrote down, this is just from my memory, but we can probably, let's see, if, yeah, can I do this? Can I derive this equation? Maybe that's the confusion you're pointing out. So let's say this is my,
Maybe we can do it
equation,
later.
and-
Maybe you may want to first go ahead with your this thing and then you
yeah,
can
let
come
me
to it.
attempt for a few minutes, and if I'm not able to do it, then we will see.
Mhm.
So this is the standard origin, but now I'm keeping foci as my origin. So that's my R. And this is another distance. That's the same distance, alpha and beta, correct? So
Beta.
you would say
Hmm.
alpha is R now, plus
Hmm.
beta is equal to 2 times A, correct? That we already argued that that is 2 times A. What will be beta equal to? Beta is, so that's angle theta now in polar coordinates, and beta will be so the height would be r sine theta. So it is r plus beta will be this length here. So it is r square sine square theta, square root of that. And this distance is, I guess this time, this is 2 times f. And that is a, so it is a plus f. Help me. So that's r cosine theta. I want this distance out. Help me here again. Okay, so draw this again once more.
You want the distance
Is it
from
not
the one of the
possible?
foci to the ellipse, right? To the ellipse which intersects at x-axis.
Yeah, I was just thinking this is my beta, right? That's my distance beta. And beta will be this square plus this square. Can I get this? So this is this square, this is r. So that's the angle theta. That's r, right? So r sine theta is this distance.
Yes.
So beta would be this plus this.
Is it
and
not
the
easy
center,
to use? Is it not easy to use the angle formula instead of trying to use the Pythagoras? Like if you want to find
Sure,
that
sure.
angle,
What's the angle formula? So you would say, oh
Like-
yeah, so you're saying, oh yeah, use the cosine angle, the cosine law, you're saying, correct?
yes.
Yeah, I see.
So beta
So
square is
maybe,
equal to
you're
your-
right. Yeah, that might be just straightforward. Yeah. So if we use the, so help me. So this is
So
2
beta square is equal
Yeah.
to
So 2 times f square plus r square minus beta square is equal to,
why do you write like that? Just write minus 4 times f times r cosine of theta
what?
equals beta square. So beta square, like I mean, take the beta square to the right. Yeah, minus 2, like, okay, Shajesh, here 2f quantity squared per plus r square minus 4 fr.
Cosine theta.
Cosine theta equals beta square.
Okay. Right. And what was I doing? I need alpha beta. So how does this help me? Probably, yeah. This is what I want, I think. Why did we go here? Yeah,
You were
I was
trying to
wanting
derive that equation.
alpha plus beta is equal to a constant, is equal to 2 times a. Right. So I have a length beta now in terms of this. And I need alpha also now. And alpha is r, right? Alpha is r. So
The top right equation you wrote, right? Alpha plus beta equals to a. So you have
that's
to
the
probably-
equation of an ellipse, right?
Yeah, so you have to again like a square and do everything like somewhere your eccentricity will come out.
Yeah, I'm not seeing this. Yeah. Like this completely throws me off.
You will use your f square equals a square minus b square, right?
I don't know.
Like that condition you will not apply, like f square equals a square minus b
We
square?
we can.
So I don't understand like why it is so difficult. Like, I mean, just follow it through and
Because I'm not seeing the alpha coming in.
not
So
here.
want me to substitute.
You don't have to put alpha here. Like you will have to substitute this entire thing in your equation.
Like this is not my equation of an ellipse, correct?
No,
We
this
agree.
is not. You will have to substitute beta in your equation.
Yeah, which is a square root of that.
Yes, and it will take the same amount of effort you did for the Cartesian coordinate.
Yeah, which was a few steps. I mean, that was
like, why do you think this should be a straightforward stuff here? But I can already see
sure.
eccentricity. Like, I mean, it is coming out straightforward.
What is straightforward? I can proceed now. This thing.
Like if
see through it?
Like I'm not seeing through it, but I can see E. I can see E coming out. If you substitute F.
Help me here.
If you substitute F equals the square root of a square minus b square. And you can pull your a, you can pull your a square out also, so then it will become, and then you can define that as E.
Sorry, I had a visitor in my office, so.
Oh, sure.
No, that's okay. That's okay. So yeah.
Yeah, I'm a little lost here.
So could we find using that cosine formula for the sides of a triangle?
Yeah, that's what we used here, but I'm a little lost as to how to proceed from there to get, like, I claim that, so this was just a claim I made, that equation of an ellipse in polar coordinates with this as the origin is that, but I'm not seeing that.
So basically we need to write alpha and beta in terms of this A, B and theta, right? And alpha. So this is your beta square.
I think you have to go through it, Shajesh. You're just like giving up because you want to look for a direct result here.
No, I'm fine, but I need to at least have a feel for it, right?
Okay,
tell me.
The point is, you have an equation. You have to do the same kind of thing you were doing in the previous one. Like there is an alpha, there is a beta. You have to substitute your beta in there. You have to square it again. Like why it is so difficult for you. So you have, like, just write beta from there, that equation. Beta is equal to 2a minus alpha, right? Or R.
So beta is equal to 2a minus r.
Yeah, now square it.
So beta square is 4 times a square minus b square plus r square. R square cancels. Okay, this is it. Yeah. So let me keep this as f. Doesn't matter. R cosine theta.
I was saying
that's equal to.
I was just saying
4a square plus r square minus 4AR. 4A square cancels out, R square cancels out. Correct? I think that's all we need. Yeah. So this is minus 4B square minus 4F R cosine theta. In fact, put this on the other side, and that's minus 4A R, right? 4 cancels out, and I have R, right? So R is equal to 4
You want to change
cancels
the
out, so it's
sign
B
also.
square divided by A minus F cosine theta. Correct? Divide it out, and so this is equal to B square over A over 1 minus F over A is equal to B square, no, A square minus B square, right? So A square minus B square over A, and that's nothing but E, I suppose, right? So that's E. That's E cosine theta, which is exactly what we wrote down here.
Yes,
Correct? Yeah,
exactly.
so that helps. Yeah.
Correct.
Okay, great.
Yeah.
Okay. Yeah. So we have these two equations, algebraic equations for the ellipse. Yeah. Okay. And now the idea is that can we proceed and get the circumference in the same spirit
But
as we did.
this was, I suppose,
for-
quicker than the rectangular one, right? I mean,
Tell that again.
this was quicker than the rectangular one. The algebra
Oh, yeah,
was
yeah.
less.
You were saying that, yes.
I am
the-
not
Oh,
sure.
was
not
this
sure.
equation is,
I'm
yeah,
not
in a
sure about
sense-
that, Rishi, because like there is like the F needs to be derived using the rectangular coordinates. That expression A square, square root of A square minus B square, like you have to go back to the rectangular coordinate and then get that A square minus B square from there. So, there,
we will have
so you
to
have
make
to
use of
know-
the.
like, I mean, how do you define your F as A square minus B square? Like A and B are defined in the Cartesian coordinates.
Yeah, so the idea
I
is
think
not
we
to
should be
not
able
use
to
the
derive
Cartesian
using the
coordinate.
initial condition. Yeah, we should be able to use it using we didn't use rectangular coordinates there, just initial conditions, right? So for example, what is F, right? F will be the distance between these 2 points. That's your 2 times F. And you would say that at theta equal to 0, yeah, alpha, like
You have to
I
define
don't
your
think
A and
we
B,
need
right? A and B are defined in Cartesian coordinate, like, or rectangular coordinate. Like
No,
A
I
and
can
B
say
are,
my-
I mean that's a geometric property, right? That has
Yeah.
nothing to do with coordinates. A
Yeah.
and B are just scales, right? The length of the
yes, the width and the
ellipse.
length, yeah.
Like extreme longest length and the
Yes.
shortest length, or something like that.
so basically,
think
like
we need
all you can do is leave your expression, like you leave your equation at F and forget about A square and B square, like A and B basically.
But
Yeah,
A
so
and B
you're
have natural
suggesting how do
scales
we
in the
get
problem.
the equation for F, right? So let's see. So we have just geometrically, let's see what is F. So there is 2 points, right? And that's your alpha and beta. This is all we have at this point. And this is R if you want. So that's alpha and beta, and this is 2 times F, correct? And this will be A in a sense. So this whole distance will be A plus F. Right? So at alpha plus beta is a constant. So we can say that 2 times alpha will be A plus F plus A minus F, right? Right away, whatever we were doing earlier, right? A plus F, this one, and this is A minus F, that's equal to a constant. So I know the constant is 2 times A. Right, so that was one of the equations we needed. And now we need the F equation. So again, go to the center point here. So there is this relation that this is 2 times F and this is alpha. So in one particular extreme situation, this is also true. And this point here, this height you say is B. Correct? So 2 times alpha was a constant, so it is 2 times A, right? 2 times A, the whole square, plus B square. No, 2 times A, the whole square is equal to B square plus F square. Why did I get the, oh, there is no 2 because this is only one of them. Is that clear how I got that? So maybe I can do this again. So first I derived that. So in this particular scenario, so this is our ellipse. Like in this particular scenario, that's your B. So that's the relation. Alpha and beta are the same. So 2 times alpha is equal to 2 times A. So in this case, alpha is equal to A. So A square is equal to B square plus F square. Right, that's F. So we don't need to depend on the rectangular coordinates in a sense. Right? And once we know
Shajesh.
these two, then
Shajesh, the point is that even when you are dealing with polar coordinates, you need a direction to define your theta, right? And that direction is taken as x-axis. So that's perfectly all right, because here, whether you call this B as Y or B, the fact is that, in an ellipse, there is this special points, where the curvature is maximum and minimum, right? The theta equals 0
but
and
I
pi.
want to stress that this is not Y, notice. The origin is here in polar coordinates.
True.
In
Exactly.
rectangular
This is not
coordinates,
Y.
we put our origin here. So that's not
Yes.
really Y in a sense.
But the point is that in the polar coordinates, your this long axis of this ellipse is your actually x-axis in polar coordinates. Your theta is defined with respect to some axis, right?
Correct.
So I mean, polar coordinates is, it's not that you cannot use the axis of Cartesian coordinates to define, because your theta is defined from the x-axis. Even in the spherical polar, you have the z-axis from which your angle theta is defined, right?
Correct.
And the angle phi is in the planar xy plane. So polar coordinate is not that it's a taboo to use xy coordinates.
Sure. I agree.
Yeah.
But I thought the point was that if you use this, then there are fewer number of steps in a sense.
That's my point. That algebra was straightforward here.
But probably the point is that now if you start from here and go there, then probably it might be the same number of steps, I guess.
I don't know.
Eventually there will be some conservation of the number of steps. Yeah. But okay.
Going from one coordinate system to other coordinate system is never guaranteed to be easy, If you
But
say
I am not talking about
X,
going
Y,
from one to another. I'm not talking about going from one to another. I'm saying like even deriving in this coordinate system, there is enough number of steps to go through.
Sure.
But anyway, I think it is a long digression. I think you should get back to the circumference.
Yes.
And it is already like an hour.
Yeah, okay. So let me very quickly now do the actual. So if we want to get the circumference of a ellipse, so the circumference of an ellipse, again, now we are in rectangular coordinates. So that's the piece we have, and the idea is that it's 4 times that. There is complete symmetry there. This is y, that's your x. Somewhere here is your x comma y, and that's point B, and that's point A. And the equation is, as we said, x square over a square plus y square over b square is equal to 1. If I solve for y, I have b times 1 minus x square over a square. Right. So the circumference would be 4 times, by symmetry, I just need the length of this curve. So that's ds. I say is just integrate over the whole thing. It's good to write it in terms of x, exactly like we did earlier. This is equal to 4 times integrate over dx, and it is 1 plus dy. So the slope, information about the slope everywhere on the curve gives us the an idea of the perimeter. And now this time we have to go from 0 to a, right? So 0 and a. What is dy by dx? Exactly like earlier, you can calculate this. This is equal to b times 1 by 2, and this is minus 2 times x over a square, and 1 minus square over a square. Correct. So that's 2 cancels out, and I have a b over, so this is minus b over a times x over a. So just conveniently written in this form, nothing special about it. But I'm interested in the square, so the negative sign goes. One could also argue that, oh, this is y is equal to plus or minus there, but I'm taking the positive root there because I'm talking about the first quadrant in there. So this is equal to 4 times 0 to a dx 1. I'm squaring this, so it is plus b square over a square, and then there is x square over a square divided by 1 minus x square over a square, right? And there is a square root of this whole thing. Same idea as earlier for the circle. We simplify this, but this time they don't cancel out. Earlier when we did this, b and a were the same, that's equal to 1, and it turns out that that cancels, but this time it does not cancel. So what we have is 0 to a dx, and this can be written as 1 minus of x square minus a square is there both places. So this is 1 minus b square over a square, and divided by 1 minus x square. Seems slightly a lot of clutter, but let's substitute. Remember that this was nothing but e square. If we did not encounter e square there, we can define this to be the e square. It's called the eccentricity of an ellipse. And then let's substitute x over a is equal to sine theta. So that dx is equal to a cosine theta, and this becomes then 4 times, when x is equal to 0, theta has to be equal to 0. When x is equal to a, theta has to be equal to pi by 2. Dx is a cosine theta d theta. This is 1 minus x over a sine theta, and this is e. So this is e square sine square theta. And in the denominator, that's 1 minus sine square theta. Is that algebra clear? Cosine theta cancels out with the 1 minus sine square theta. And what I have left out is whatever is remaining is equal to, put this. So this is exactly what we followed in the steps that we used for the circle, right? Only thing that happened in the circle was that this would have gone to 0 and this would have canceled out, and this integral was really doable. So the circumference of a ellipse comes out to be equal to 4 times a times the cosine theta cancels out, and that's 0 to pi by 2 times d theta, and you have 1 minus e square sine square theta. This integral cannot be done in a closed form, but let's very quickly check what could happen. Remember, e was equal to 1 minus b square over a square. What happens when e is equal to 0? That means b is equal to a, and that's the idea of the circle, right? So e is equal to 0, and then that integral becomes doable. So that's 4 times a times pi by 2, and that's correct. So that's 2 pi r. There's one more limit you can take, at least in an extreme sense. We can think of a situation where e is equal to 1, and that will be the case when b is equal to 0. Right? So think of like this was your 2 points in the ellipse, right? And now we are considering the situation that this b really comes out to be 0. In that case, you're pretty much going the length of the distance between these 2 points multiplied by 2 is your circumference, right? That's what we should get at least. And in that case, it's basically a line segment. Line segment, but now it is wrapped around itself. So it is 2 times that line segment. So that c is equal to 4 times a, and this is 0 to pi by 2 times d theta. E is equal to 1, so this is nothing but cosine theta. That integral is 4 times a times sine theta, evaluated from 0 to pi by 2. So that's indeed 4 times a. That length was 2 times a. It is 2 times the focal length, but focal length is equal to a in that extreme limit when b is equal to 0. So that also works out. But in general, this integral cannot be done. So you actually define this to be equal to what is called the complete elliptic integral. So this is the complete elliptic integral, and of the second kind. So it turns out to be another elliptic integral, which is a k, but let's not discuss that in here. So in principle, that's an integral representation of that complete integral of the circumference of a circle. But usually it is, we also know that sine and cosine or all functions can be represented as a power series. So it's good to think of it as a series representation, and we can get what is the series representation of that. So let's think of this as expand that out. So this is 0 to pi by 2 d theta. Expand that 1 minus x squared. So this is 1 minus 1 by 2 e square sine square theta. And go to the next term, it is 1 by 2 minus, so then there is minus 1 by 2, and there's already a factor of 2 there. So that's minus 1 by 8, and e raised to 4 sine raised to 4. And you can think of higher orders the same way. Keep expanding. That's a straightforward series expansion. And now this can be evaluated. So that's 4 times a. This integral is pi by 2. That's just d theta minus e square over 2. So that's 1 by 2 times e square. And the integral of sine square is when you go from 0 to pi, that's pi over 2. So this is pi over 4. And sine raised to 4 also can be done similarly. At this point, I will just simply write that down without working that out. So integral of sine 4 theta, this was theta, is coming out to be, what was it? It is, I think, 3 pi over 16. And the higher orders. So that can be written as pi by 2, 2 pi a if you want. So that's times 1 minus e square over 4. Right? And 2 comes out, so that's 64, right? So that's 3 by 64 times e raised to 4 minus, which is the standard power series representation for the complete elliptic integral if you want, with that pi by 2, or that's one way you can proceed. And either you can represent a function using the power series representation or an integral representation. So that gives us the circumference of an ellipse to whatever accuracy you need, correct? How much ever significant digits you need, you can put that in. And yeah, that's what I wanted to do. Yeah.
Mhm. So basically you're saying that like the circumference of an ellipse is going to be smaller than the circumference of a circle, which is made out of radius a, like semi-major axis,
Yes.
right? This is how
Correct.
your power series is coming out to
Yeah,
be.
that makes sense, right? So that will be
Right.
your,
Which means
right,
that there
that will
should be
be the
another way
circle
of,
of,
yeah, which means that
one
there
can
should
also fit another circle like this,
be, true.
right?
Yeah.
In terms of B, it will be larger than that. Yeah, correct. Good point. Yeah.
Like that's how your
Yeah,
power
I agree.
series expansion is coming out to be. And I think, isn't there something related with these two circles, like ellipse? I think whenever we were thinking about drawing ellipses, like this, there was a method of drawing it between these two circles, right? Like what you keep between these two circles that will define the trajectory of, I don't know, like I forgot it now.
Yeah, I know what you're suggesting. I also don't remember. Yeah.
Yeah, I mean, I guess, yeah.
Rishi, did you have to miss? There was.
Yes, yeah, no, in between again, I had some other visitors, so I closed my video. Yeah, yeah. So,
Okay.
yeah, so I think this, the lack of closed form is the price we pay for the eccentricity of the ellipse.
True. True.
So
Yeah, that's a good way of
eccentricity,
saying. Yeah,
eccentricity
leads
is the price,
to
right?
this. Yeah, that's a good point. That's a good
Ellipses
point,
are
right?
eccentric. They refuse to be closed into a
Yeah.
form, you know.
Yeah. Why should they conform?
Yes, they are eccentric, you know. you put the eccentricity to
Funny.
0 and then they will work out. They will nicely.
Correct. Yeah. Yeah. Closed form in terms of this elementary functions like sine and cosine.
Yes, yes.
Like once you accept this to be a function too, then this is a function.
And I mean, I think I'll concur with Prachi that perhaps I think there may not be much difference when you do it in Cartesian or polar, because ellipse being eccentric, so they do not truly exploit the circular geometry, right? I mean, because anyway you have r and theta both varying, right? So
Sure.
so just as you have x and y varying there, you have r and theta varying. So technically there isn't, but maybe perhaps if I haven't ever used this elliptical coordinate systems. So
Yeah,
me either.
elliptical coordinate systems. Now that is
systems
something.
might,
Yeah,
that might make things simpler there.
probably.
Yeah.
But I've never ever used elliptical. I've never gone beyond this spherical, polar, cylindrical.
Yeah, I think that might be. Yeah, I have
Because
not
it
been
exploits
to-
the symmetry, this.
Correct. Yeah. And we can try this cosine theta integral, but again, that will be an integral in 1 over 1 minus e cosine theta. That I mean, that's not standard integral. We'll have to do contour integrals. Correct. If you do this, if you go to the polar coordinates now, if you do polar coordinates, so then we have this as our equation. Right. So then our circumference will be equal to the. Actually, we don't know, right? We also need
Don't know.
dr now, right?
Mhm.
Yeah. We
Yes,
need
yes.
ds.
Yes.
Right,
Now
we
it is a
need-
general formula.
Yeah. So dr square plus r square
D theta square.
d theta
Yes.
square.
And then you have to go all the way 0 to 2 pi.
Yeah.
Hmm.
So yeah. So that's not
If you're doing
straightforward.
the
Yeah.
depending on
So
yeah,
d
the
theta.
technical-
So it is 1. That is r. Yeah, 1 plus dr over d theta. I think that's what it will be, right? So we need to take the derivative of r with respect to theta, and that will give me a sine theta in the numerator and the square of this. So it's, yeah, I think it's good to attempt this. Yeah.
Yeah, maybe.
But
yeah.
I think we should stop here, I guess. Now it's already 12,
Yeah.
20, unless.
Yes.
Yeah. I can
I'll
try
have to
that.
go
Yeah.
home and take lunch and come back for the invigilation.
Invigilation. Okay. Yeah.
Yes, it's a 3-hour.
Okay.
Mhm.
Okay. So.
See, this is Shajesh. What is the duration of